Good. All right. So we are not going to be able to cover everything tonight because there's just too much to review for a final. That's why I threw all those multiple choice questions on there, mostly to hope when you saw it, it would remind you there's a lot of other stuff. The first, I think 5 questions, I didn't put a key on there for, maybe 4. So we'll probably look at those, and then any multiple choice you have a question about, we'll talk about those. Most of it comes down to using your formula sheet. There it is. Oh, which is not very happy looking here. I think so. Well, you have these too, so yours will look a little bit nicer. It just didn't like the PDF, I guess. All right, well, let's go ahead and start. So, on many highways, state police officers conduct inspections of driving logbooks from large trucks to see if trucker has driven too many hours in a day. At one truck inspection station, they issued citations to 49 of 348 randomly selected truckers that they reviewed. Assume that trucks were chosen randomly for inspection. Let's get a 95% confidence interval, interpret it, and then there's another question about margin of error. Okay, good. So, is this for a mean or a proportion? Yeah, how do we know? Okay, yeah, 49 out of 348, that's good. How else do we know it's a proportion? It says proportion. It doesn't always say proportion. If it's about a mean, it's going to have the word mean or average. For proportion, it doesn't always have to. Now, I think you've already answered the question. Is this a hypothesis test or a confidence interval? And I've already heard it's a confidence interval. Okay. Now, if you're worried about these, you know your calculator can do them very, very, very fast. So I'm going to do that first, and then I'm going to do what I would actually do on a test. So I would go to stat, tests, and this is a 1 proportion Z interval. So I'd go way, way, way down. 1 proportion Z interval. Number of successes, X is how many? How many successes we got there? Yeah, out of? Good. Oops. And look, it gives us our confidence interval. The answer comes so quickly. Okay, so we can always check ourselves that way. Now we're going to do it the more involved way to make sure we get all of our points and we understand what's going on. So if we are doing a confidence interval, what's the first thing we do? Conditions. Yeah, absolutely. If we're doing confidence interval or hypothesis test, we need our conditions. So to find those, I look at my formula sheet. It's going to look nicer on yours. Proportions are on the front page. Means are on the back. We are doing a confidence interval. And on mine, it looks just terrible. So I'm going to have to write it out separately. But on your formula sheets, you know what it looks like. And I'll write it down here too. It's the one that should say p hat plus or minus z square root p hat 1 minus p hat over n. Okay. That's the formula. Now the conditions are always parenthetical. So it says a simple random sample with the number of successes and the number of failures in the sample, each 15 or more. So I'm going to go back to that other one. And think. So I can say conditions. This is a random sample. there are 49 successes. And let's pretend I wrote that better. And how many failures would there be? Yep, perfect, Mikhail. You do 348 minus 49, and that is, what is that, 299? So both are well over 15. So we can keep going. So first you identify, is this about proportions or is it about means? Is it a hypothesis test or a confidence interval? And then you just look at the formula sheet. First thing it's going to tell you in the formula sheet is, in parentheses, conditions. Write down if they're met or not. And then you go to the formula part. That one. So the formula we had on the formula sheet, and again, it just looks like this: p hat plus or minus z square root p hat 1 minus p hat over n. And at this point, we know what p hat is, or if we don't, we can find it very easily. P hat is, how do I find it? Perfect. 49 divided by 300 and what was the other number? 48. Perfect. And so if I'm going to round that, typically how many decimals am I going to take that out to be? Good. So that is 0.1408. So I can put that in the formula here. Plus or minus some number. I'll just leave a blank for a second. P hat again, 0.1408 times 1 minus 0.1408 over our sample size. What was our sample size? Yep. Now, how do I find the number that goes right here, that critical value? Yeah, it's based on the confidence level. What is our confidence level for this problem? 95%. So I can find it by doing what? You can look at the formula sheet. Yeah. So if I do that, it's right here, 1.96. Now, I've found some people to get confused by this, finding the number on the formula sheet, because when can I not use this number? When it's for t, when we're doing it for a mean, right? And so then they're like, well, when do I do the t inverse? When do I do? You can always use the inverse function to do it, except when we're dealing with a proportion, are we using t or z? Z. So if we wanted to find that, we would use norm inverse. So I do second, distribution, inverse norm. Now, the area part, if we're talking about 95% confidence, and we're looking for the end of that lower tail, how much is left over from the 95%? Well, what does it have to, what's the total area under the curve? 100%, right? So how much is left over from 95? And then if we just want the left tail, 2.5%, right? So I could do 0.025, comma, what's the mean? If we're talking about a normal distribution for probability or proportion, standard normal 0 and 1. Good. So see how it's negative 1.96 rounded? If you want to use the more accurate value and do it that way, because you get less confused when you do it for the means and proportions, great. If you remember, I can only use the table for proportions and you use the table, that's great too. However you did it, 1.96, or you can be a little bit more accurate. Actually, that would still round to 1.96. 1.96. Okay. So I would write all that on the test. I would show my conclusions. I even write the formula because it's harder to make a mistake when the formula is there. And then I need to turn this into an interval. So I do 0.1408 plus or minus, and I'm going to put this stuff to the left, I'm sorry, to the right of the plus or minus, my margin of error into my calculator. 0.1408 times 1 minus 0.1408, and then divide by 348. 0.0365. Okay. Now, if I want the lower bound for the interval, I subtract. And if I want the upper bound, I add. So my confidence interval is 0.1043 to 0.1773. One zero four three 773. Am I done with this problem? What do I still need to do? Yeah, I need a conclusion, right? And so honestly, for confidence intervals, it's pretty much always the same, as long as you're paying attention to what confidence level you're at. I am blank % confident that blah, blah, blah. You do want to make sure that you're talking about the population, right? And you want to make sure that you mention what it's for. Is it for a mean or a proportion? Okay. So I am 95% confident that between 10.43% and 17.73%. And then I have to reread the question because I've mostly forgotten what it was about. On many highways, state police officers conduct inspections of driving logbooks from large trucks to see if the trucker has driven too many hours. Okay. Of truckers going through this checkpoint drive too many hours. Okay. Any questions about that? Yeah, Lindsay. Yeah. Yeah, so that's a good question. What did I get a minute ago when I did it with my calculator? So no, I actually got 0.1773. So were you doing it in one step like this using the one proportion Z interval functionality, or did you do all the steps like I just did?
I did.
Okay, so you do want to do the separate steps so you can show where it's coming from. So if there's a little mistake, you can still get most or all of the points. The fact that it's off by, it shouldn't be off at all because mine wasn't. Yeah. Z interval. Yeah, see, it's not 0.1774.
Yeah, and I.
Is that? Oh, and I had 0.1773. I see. Yeah. It's because Yours rounded to a different level of precision than mine did. Let me check your mode here. It's just not an issue to be off by 0.0001. Okay. If you're showing your work in the differently. If you're showing your work on these steps, it'll come out exactly the same. What happened is your calculator went out to 5 decimals. And if I took that out to 5 decimals, it would round to a 5 after that 3. And then you round again. And so there's a double rounding, and that's why it came out slightly different. Okay, great. Thank you for asking about that. Anybody else? So again, most of these types of problems, if you look at your formula sheet carefully, it tells you most of what to do. You just got to identify if it's for a mean or a proportion. Interpret the interval. Okay, so we did A and B. How large of a sample would officers need to take to arrive at a margin of error no greater than 2%? Okay, now this is the part where we go back to the formula sheet. And if we're looking at our formula sheet, this formula right here tends to hide from people because it's right in the middle. This is our sample size formula for when we want a given margin of error. And again, if you're looking at your own sheet, it's a lot prettier than this came out. The PDF conversion wasn't very happy, I guess. Okay, so just writing that out, it was in equals p hat times 1 minus p hat times z squared over m squared. Okay. Now, for that formula, unless you have a very good idea of what to use for p hat based on previous data, you should use what value? The formula sheet even tells you. 0.5. So unless indicated otherwise, we would use 0.5 for that. Now, what am I going to use for m? Yeah, because it wants a margin of error no greater than 2%, so 0.02 here. And what am I going to use for z? Confidence level, right? And so what z corresponds to a 95% confidence level? Yep. So we just got to make sure we put that in the calculator correctly and we'll be done. So here, I'm going to say 0.5 times 1 minus 0.5 times 1.96 squared divided by 0.02 squared. And that comes out to be 2401. If there was any decimal, if it was 0.1 at the end, I always round up, okay? From the margin of error desired, no greater than 0.02. Does that make sense? All right. So a test of sobriety involves measuring a subject's motor skills. The mean score for men who are sober is known to be 35. A researcher would like to perform a hypothesis test to determine whether the mean score for sober women differs from 35. 20 randomly selected sober women take the test and produce a mean score of 41 with a standard deviation of 3.7. Perform the hypothesis test at the 0.01 level of significance. Same starting questions. Mean or proportion, confidence interval or hypothesis test. Now you said very quickly mean. How do we know mean? Yeah, because it says mean. Very good. Oh, that's not a highlighter. All right, so mean, and then hypothesis test or confidence interval. Yeah, because we're told specifically that, right? The significance level is another nice tip off. So, like the last time, I'll show you the calculations aren't a big deal. You can use your calculator to test the answer very, very quickly. Before we even do that, though, let's look at setting up our null and alternative hypothesis, because really we don't want to do anything without first doing that, okay? No. So that's a great question. Typically, we check our conditions or assumptions first. If you look at your formula sheet, the formula sheet will guide you in the process. So we just said this is for a mean or a hypothesis test, right? And so we are looking right, man, this looks horrible, right here. Okay, now notice it says test statistic 4, the first thing it gives you is a null hypothesis, right? To me, that's a cute, go ahead and write down my null and alternative hypothesis. Then the conditions. Now, the reason why the conditions are typically going to happen after, if you look at for a proportion, we actually need P naught when we're determining those conditions. So for a mean, it doesn't matter. You can do them first if you want. For a proportion, we actually need what that null hypothesis is to check the conditions. Okay, so I'm going to go back and write down my null hypothesis and my alternative hypothesis. Okay, now what symbol am I going to use in this problem? Yes, fantastic, mu. And I can write that here, and I can write this. Even without reading it, I could write that as long as I know it's about a mean, because I know we use the symbol mu, and I know the null hypothesis is always a statement of equality. So mu equals what? Yeah, why 35? Yes, it's the mean for men, and we are looking at what? Is it more? Is it less? How does it relate for women? What are we investigating? So what symbol would I use? Not equal. Very good. So once I know this number, that number is always going to be the same. And then we have to just read the problem to know if we're doing less than, greater than, or not equal to. This one is differs. Differ could be less, could be more. So that's why we use not equal. Exactly. Now we check our conditions. Now, if you looked on the formula sheet a second ago, it said simple random sample. They all say that, right? And either it's a large sample or normal population. That or is a big deal. Don't just write down one of them and hope it's right. Just read it. Okay. Now, how big is the sample here? Okay, 20. Is that large enough for us to consider large? What do we consider large? 30. So no. So hopefully it's normal. Is it? Huh. Well, let's pretend. All right. So is this a random sample? Does it tell us that even? Yes, randomly selected women. Okay, so this is an SRS. So we're happy about that. Now, I wasn't super careful putting this together, apparently. And so you could answer this in a variety of ways. You could say, you know, our conditions, we don't know if they're met, so it's not reasonable to proceed. Having said that, we're not going to get a lot of use out of that. So I'm going to say, let's pretend the person who put this together was more careful and wrote something like the sample data are approximately symmetric and unimodal. Then what could we say? Normal population, probably, right? Because if it's a random sample, it's likely to be representative, and that means it's going to look like the population. If it's unimodal and symmetric, then we can expect the population to also be approximately normal. Okay, so I'm just going to write assume normal population. Typically on a test, people would be a little more careful in how it's written. Yeah. So now I can jump back to that formula sheet. And it says test statistic, blah, blah, blah. We check that, and then it says T equals, and the formula has disappeared here. But that's what we do next. And then it says p-value, and then we get our p-value, okay? So I'm going to jump back. My test statistic. Now notice it does say T equals, okay? T equals X bar minus mu naught over S over the square root of N. So what is X bar here? Okay, what is that? 41, perfect. Yes, 41 minus, what is mu naught? Yeah, that's what we said in the null hypothesis. Over S. What does S stand for? Standard deviation, sample standard deviation, right? And for us, that is 3.7 divided by sample size was 20. Okay. So I'm going to put that in my calculator. Now, some of you have calculators that'll show fractions nicely. And if you put your calculator to make it do that, that's great. If your calculator doesn't jump in fraction form for you, make sure you put parentheses around your numerator. Otherwise, the calculator is not smart enough to know when the numerator starts and stops. And I'm going to put parentheses around my denominator. Square root of 20. Oh, that's a pretty big number, 7.2521. And then right after, when you look at the formula sheet, it says get your p-value from your t distribution with df equals n minus 1, right? So I know I'm going to do something with what command? T-CDF, that's right. For this class, we're going to do a lot of normal CDF, T-CDF, inverse normal, and inverse T. Those are the ones we use over and over. So this one's T-CDF. And it's lower bound, upper bound, degrees of freedom. Now, a picture here might help. We always assume that the null hypothesis is true. That's our center value. What we've done is we've said, okay, if that's our 35 here, then we're going way out to 41. That's actually 7 standard errors out, okay? So if we think of this at being at 0, this would be at 7.2521. Our p-value would correspond to almost this area. How would that area relate to our p-value? We'll get there when we get there. How do I find that area? Then we'll talk about how it relates to the p-value. Are you using the table in your class? Okay, you could do that, absolutely. And it's going to be off the table, right? And so it's going to tell you it is tiny. It's going to be about 0, right? Okay. If you are using your calculator, you would use negative, actually, that's not what I would use for my lower bound. That's just what the calculator suggested. My lower bound would be this 7.2521. What would my upper bound be? Sure, and I'll just use 10 to the 99. Any really big number will be fine. How many degrees of freedom do I have? I have 19. It's always sample size minus 1. That's right. Now, that would typically give me the p-value. If the alternative hypothesis here was greater than 35, that would be the p-value. But because it's not equal, what do I need to do to that to get my p-value? Multiply by 2 because we're talking about both tails, less than and greater than. Because the curve is symmetric, if you have 1, you can just multiply that by 2. If I were you, I would actually write down where this is coming from, because then if you slip on your calculator and put in a wrong number somewhere, you still might be able to get points. And so that equals, and I say that 2 times that, I'm going to say times 2 here on my calculator. And it gives me about 7 times 10 to the negative 7.
We've got a question.
Yeah.
How do you get to the page distribution on the calc?
Yeah. Second, distribution is above the variables button, the variables, VARS.
Okay.
It's right next to your arrow keys. Draw on this. Nope.
Nope.
So, we've said take everything to 4 decimals very often. What is that to 4 decimals? It's 0, right? Because that means 0.0000007, right? So to 4 decimals, that's about 0. That's tiny. Okay. So that's where the formula sheet stops helping you. It gets you all the way to the p-value, and then there are 2 steps left: decision and conclusion. Okay. Our decision is about the null hypothesis. Our conclusion is about the alternative hypothesis. And if you know one, you know the other. So the little trick to help you with the decision is if the p is low, the null must go. Okay. So by any standard, that is a tiny p-value. What do we compare the p-value to decide if it's big or little? Significance level. What significance level are we working with here? Yep. So is that smaller than 0.01? Yeah, a lot smaller. So since our p-value is less than 0.01, either I reject the null hypothesis or I fail to reject the null hypothesis. Yeah, you reject. Very good. Reject H0. And so that's my decision. The conclusion comes from that. If you reject H0, what's left over? The alternative. And so I try to write that in the context of the problem. There is evidence that, and then I read the question again. It's about sobriety test. We were wondering if the score for sober women differs from 35. And so we're saying, yeah, it does. There is evidence that the score, the mean score for sober women is different. Now, if I wanted to check my answers really quickly in my calculator, I could go here and I could say, all right, let's do stat tests. And that was for a proportion. So that'd be a 1 proportion Z test. And I'd get an advertisement, which is the one good thing about your calculator. It doesn't do that. And then, just your number, your null hypothesis, which we said was, oh, I did it for a proportion. That's not right, is it? What should I have gone to instead? Yeah, so that would be a t-test. And we could do our null is 35. Sample is 41. Standard deviation is 3.7. Sample size is 20. Not equal to. And see, Yep, it's going to give you the wrong answer if you put the wrong thing in there like I did. There we go. There it is. So same test statistic, same p-value. We're happy. To help you remember when to use which function, probabilities are areas, right? And so anytime we're talking about a probability, we're talking about either our normal CDF or our t-CDF. And so that comes up when we're finding p-values. Normal or t, depending on proportion or mean. We use the inverses when we're finding our critical values for confidence intervals. Means we have to do with the calculator, that's T inverse. Proportions, you can use the table or use the normal inverse. Okay, so that's the difference between those buttons. Are we okay with this? Okay. Can I clear it off, or are we want to talk about part of it, or just have me shut up so you can write it down? Okay, good. So let's delete it. And now that was that whole problem. The weights at birth of 5 randomly chosen baby orca whales were 425, 454, 380, 405, and 426 pounds. Assume the distribution of weights is normally distributed. Find a 95% confidence interval for the mean weight of all baby orca whales. Interpret that interval. Okay. Fantastic. See, you even know what I'm going to ask. It's about a mean, right? And we know that because we see the word mean. Let's see. Where do we see it? Right there. Mean weight. And we see confidence. Okay. So you're exactly right. We look at that part of the formula sheet. It's a mean. So it's on the second page. It's confidence interval. So first thing we do is check what? Conditions. Absolutely. Where would I find those conditions if I didn't know them? Yeah, they're in parentheses right there in the formula sheet. So this is for a mean. So we are right here. Simple random sample from an approximately normal population or large simple random sample. Is this a large sample? No. Is it normal? And this time it actually tells us. This is an SRS from a normal population. So we can proceed. Then for confidence interval, I find the interval using the formula. And again, that's right there in the formula sheet. And so I write the formula, x bar plus or minus t s over the square root of n. Now, I would say if I had to pick the most common error for 215 students to make on the third exam or sometimes the final exam would be right here. And it's picking the wrong value for t. So take a minute right now to see if you can find the correct value for t. If you can do that, you can do the whole thing, I'm sure. Now, if you put 1.96, you would be making that common mistake. How do I know it's not going to be 1.96? That would be the value if I was talking about a proportion and using z. It says t there, so I know it's going to be different. Now, if I think about the difference between the distributions, if you know the details in the t distribution are higher, and so I know it's going to be a little bit bigger. The larger the sample size, the closer it'll be to that 1.96. This is not a super big sample size, though, so it's not going to be right at 1.96. How do I find it? I hit second, distribution, and what do I use? Exactly, inverse T. So area, now for inverse T, what area am I going to be curious about for a 95% confidence interval? Close. Okay, so 95%. So we're talking about the middle 95%. And so we look at the tails, right? How much is left in the tails when we're talking about the middle 95%? Right. 0.05 total, but we cut that in half because half's in each tail. So 0.025. And then how many degrees of freedom do we have? Here we only have 4. So there we go. So if I'm putting this in, well, I need to find that mean too, don't I? How do I find the mean? And the standard deviation? I would, absolutely. Yeah, how do I find those things? Stat, edit, another advertisement.
We are water, reaching new shores.
Nice. So we just put our data in, right? 425, 454, 380, 405, 426. Okay, not a lot of numbers, so it doesn't take much time to do it. So if I want the mean and standard deviation, I hit stat. Then what do I do? Yep. And I mean, you could use the formula for them, right? You could add them up and divide by however many to get the average. You could use the standard deviation formula too. This is way quicker though. So I see here my mean is 418 and my standard deviation. What's my standard deviation? So I see 2 standard deviations. Which one do I use? Do I use the 27.4864 or do I use the 24.5845? Yes, because it's the sample value. We're always using the S. The other one's for the population, and there's definitely more than 5 orca whales. So 418 plus or minus. Now we said T was 2.7764, and the negative doesn't matter because if you add or subtract a negative, times, and our standard deviation we just said was 27.4864 over sample size square root 5. Don't forget that square root down there. So that's 418 plus or minus, and I'm going to do that right now, 2.7764 times 27.4864 divided by square root 5. That gives me my margin of error, 34.1283. And so my interval, does the order matter in which I do them? Like which one has to go on the left? The smaller one, right? Because it represents an interval and intervals go from smaller to bigger. So I would say 418 minus 34.1283. That'd give me my lower bound. And my upper bound, same thing, but with a plus. Done? Yeah. I hit stat, edit. I put in my numbers in list 1. And then I hit stat, calc, and I did 1 variable statistics. That gives me the mean, it gives me the median, it gives me the standard deviation, it gives me all kinds of stuff. You can get your 5-number summary from that too. Okay, are we good with that? Then we need our conclusion, and don't say something like there's a 95% chance or something like that, because when we use confidence, we use it in a very specific way. We're being kind of lazy when we say we're 95% confidence. What we're talking about is the procedure, not the specific interval. So we don't want to say 95% chance of anything, because we're almost definitely going to say something false. We do want to use 95% confident in our expression because we've taken that to mean a certain thing. I am 95% confident. Now, one way people miss this is they forget to say what they're talking about. Okay. I'm not confident that orca whales weigh this amount. I'm confident that the mean weight of baby orca whales is this amount, right? So the word mean should be in there. That the mean weight of baby orca whales is between, now I'm gonna have to write on the other paper here, 388, 3.8717 and 452.1283. Now, if I wrote that, it'd be pretty good. It'd be a little wrong. What am I leaving off? Units, exactly, pounds. Good. Okay, I want you to take a minute and look at the next problem because it's a little tricky. Try to draw a picture for it. You know, the longest review is the one I'm running the most on time for.
Congrats.
All right, so let's see if your picture matches what I'm gonna do. A box of Raspberry Crunch cereal contains a mean of 13 ounces with a standard deviation of 0.5 ounces. The distribution of the contents of cereal boxes is approximately normal. What is the probability that a case of 12 cereal boxes contains a total of more than 160 ounces? Wow, there's a lot going on in this problem. Any idea? $13 is the mean, yes. This is a tricky problem. What? It kind of. So that's for the population. What could you consider these 12 boxes to be? A sample, absolutely. So actually what we're going to think about is the sampling distribution of sample means for all of the cereal boxes. Okay? What would they be centered at? If I took a bunch of boxes and I took the mean amount of cereal in them, what should they be centered at since we know the population value? 13, yeah, we know it's an unbiased estimator, so it's going to be a little less or a little more, right around 13 though, right? So that's very good. What's not going to be the same is the standard deviation, right? And the idea here is it is not surprising at all for me to find someone on campus if I randomly choose and I end up with someone who's 6 feet tall. But if I randomly pick a class and the average height is 6 feet tall, that would be very shocking, right? Kind of the same when we're talking about a sample versus an individual. Standard deviation is not going to be 0.5 here. How do I find it? There is. Where would I find that? It is on the first page of the formula sheet. You're exactly right. What words am I looking for? Yes, that's partially. Yeah, I mean, yeah. Sampling distribution. Now, am I doing it for a proportion or for a mean? Yeah, so it's right here. And again, it came off a little poorly here. It's centered at the true mean, this nice central limit theorem we're talking about. Now, what is the standard deviation when you look at your formula sheets? What's the formula? That's for a proportion. Yeah, population standard. So it's sigma divided by the square root of n, right? Yeah. Okay, so I'm going to do 0.5. Oh. And get 0.1443. How on earth does that relate to what the question's asking? The probability that a case of 12 cereal boxes contains a total of more than 160 ounces. So we're talking about single boxes, right? How could I take that 160 and take it into something that's like a single box? Okay, yeah. So what would 160 divided by 12 be? 13.3 repeating? Great. So we're looking at what's the chance of getting a mean from those 12 boxes of 13.3 repeating? Right? Or what's the chance of getting a sample at least that extreme? So, any idea? It's an area. How am I going to find an area? Perfect, normal CDF. So the probability of getting a sample mean of at least 13.3333 equals normal CDF, and it's going to ask for our lower bound.
Native deodorant is my go-to when noodles rushing me to get out the door. Keeps you smelling fresh for 72 hours, and the scent is to die for. Also loving that they're aluminum-free and cruelty-free, having a pet myself. Then I leave my house with full confidence because you know.
Lower bound is, what's the lower bound? Yeah, 13.3333. Upper bound is infinity, which we're just going to use a really big number because our calculator doesn't have an infinity button. And then the mean is, what's the mean? I'm so glad you said that. That's what I wanted someone to say. We use 0 and 1 so often because when we're doing hypothesis tests, we found the number of standard errors. So we're looking at the standard normal table when we find those values, right? For this one, we are looking at this distribution. And so that would have a center or a mean at 13. And then the standard deviation. What's the standard deviation here? It's the 0.1443 because we're talking about what's the chance of getting a sample of 12 boxes with that mean weight. If you wanted to use 0 and 1, you could. What you would do is find how many standard deviations the 13.3 was away from the 13 using this. You would find the z-score for that, right? Just like our test statistics when we're doing hypothesis stuff. So anyway, it's that number. 0.0105. So pretty small, about 1%. Oh, someone just said it out loud, so I assume that was true. We want a mean of what to give us 160 ounces. Well, if you divide 160 ounces over 12 boxes, that's 13.3333. So we're saying how likely is it to get a mean at least that much? Now, to me, inference is a major point of the course. So you need to be able to find confidence intervals and do hypothesis tests for means and proportions, for sure. Now, what else is there? All kinds of stuff. Yes, I have a hand up. Beautiful question. So the question was, why did I use normal CDF instead of T? And it's because we were told the population is normally distributed here. And so the central limit theorem gives us an idea that the sampling distribution is going to be normally distributed as well. We use T in the context of confidence intervals and hypothesis tests, specifically because for relatively small sample sizes, it gives a better result when we don't know the population standard deviation. This is the one instance where we know the population standard deviation, so we can use the normal curve. In the context of a confidence interval or hypothesis test, you don't usually know what the population values are. Otherwise, why would you bother with the confidence interval hypothesis test? Does that make sense? Beautiful question. Okay, so all that multiple choice stuff, hopefully you had a chance to look at. Someone actually emailed me about one of the questions. I pulled these questions from a lot of different textbooks, and the method or procedure for finding quartiles is not universal. There are differences. Some people include the median when they do it, and some people exclude the median. And so one of these questions, the key is actually different than what it should be. For number, it's actually probably quicker if I just look at the key. Nope, it's not. This one. For 29, the answer should be B. the answer in the key uses a different procedure than we do, which would give us another outlier. Now, what I wanted to do in the last half an hour is, if you have any questions about any of these that we've already done or that we haven't talked about, that's what we can talk about. Yeah.
In my class, we've been doing this by hand, not figuring out how to do it on the calculator.
Yes.
So I'm kind of confused with that. It's new to me.
Yes. So at least two of our sections have eliminated tables. And so if you haven't, you're going to do things a little differently, right? Where I use normal CDF, you're just going to use your Z table, right? Your standard normal table. Where I use T CDF, you're going to use your T distribution table, right? And where I found my critical values, you would just use your T distribution table going up to the degrees of freedom, right? What else we got? Any questions in there that look scary? Like, I know you probably haven't done them all, but look at them and go, which one do I really not want to be on a test? 6? All right. Anything with pictures? I don't remember what 6 is. Let's see. Oh, I mean, does it look like those things are, does it look like there's some type of association? Is it approximately linear? Yeah, I mean, it looks roughly linear, right? Is it a negative or positive association? Yeah, it's negative because it has a negative slope, right? And the correlation coefficient has the same sign as the slope. And so if I wanted to describe that, I would say there is a strong negative linear association. Now, when there's the linear association, we can give a correlation coefficient R. Now, we talked a little bit about calculating. We pretty much always had a machine do it for us, right? So this one, I just eyeball it. So I use the word strong. What would be a strong value for R? So what's the range of values for R? 1 and -1. And so you're right. Strong means close to 1 or -1, right? That's very good. Weak or 0 is no linear relationship, right? And so we said it's strong and it's negative. So pick a number. Sure. That's a good number. -0.8, -0.9, -0.85, somewhere in there, right? If you look at the key, I think I gave a range of values that I thought are a pretty good guess. The most important thing there is that you recognize it's strong, it's linear, and it's negative. Yeah, and? Yeah, so if you wanted to do it on your calculator, it would be very hard to do with this because I don't have the specific values. But if you have the values, you just go to stat, edit, you put your X values under list 1, your Y values under list 2. And then if you do stat, calc, lin reg, it'll give you your coefficients and your R and R squared. If you've been doing it that way in class, you probably already have R and R squared where they work. If you try it and it doesn't give you R and R squared, I can show you how to get that. Okay, what else do we want to look at? 14, sure. Oh, yeah. Great. So interpreting slope is one of the parts that people tend to have more trouble with in a linear regression. And so when I look at this equation, the most important thing when I'm doing this problem is being able to identify the slope. Which number in this problem is my slope? Yes, you're exactly right. It's the one next to the X. Whichever order the X and the constant are, the slope is going to be given by that number. Now, is it positive or negative? So it's going to correspond to an increase or a decrease. Yeah, so it's going to increase by that much. Now, it's easier to interpret as a fraction. What's the easiest way to make any number into a fraction? Yeah, so 4.842 over 1. If you throw the units on there, it's even easier to talk about. Now, the Y units for this problem, it says is weight, so probably pounds. What are the X units here? Yeah, height. So given by probably inches, maybe. So every extra inch is going to correspond to 4.842 pounds on average. So if they grow an inch, they gain almost 5 pounds on average. Yeah, so yep, you're exactly right, D. Oh, wait, no, it's not D. We do have to read it carefully. What's wrong with D? Yeah, it says for every unit increase in weight. We're saying if we increase in height 1 inch. So that's actually answer A. But you had the right idea. Those words in there get in our way. We got to read them carefully. All right, what else we want to talk about? 30? Oh, that's really far down. Oh, sure. Yeah. So we talk about terms like sensitive and resistant to extreme values. The mean, do we say the mean is sensitive or resistant to extreme values? The mean is very sensitive to extreme values. If you throw a really tiny number in there or a really big number, it throws the mean way off, right? And so we know the mean gets pulled in the direction of skew. What direction is this distribution skewed? Okay, so if you're like me, that skewed left, skewed right seems like it should be opposite. The tail term always made it easier for me. Which side looks like it has a tail on it? It's left-tailed or left skewed. Okay, so if you think about it looking like a little dinosaur, think about which side the tail's on, and that tells you the direction of skew. So it's left skewed. So let's label the easiest one first. What's A? Oh, how do you know? It's peak, tallest point. Absolutely, yeah. And so then I think the easiest point is I know which one gets pulled in the direction of skew the most. So what's C? That's it. What's left? So B must be the median. Yeah. Does that make sense? All right. What else do we want to look at? Yeah. Sure. 35. Oh, yeah. This one actually is pretty quick. The annual precipitation for one city is normally distributed with a mean of 390 inches and a standard deviation of 3.2 inches. Fill in the blanks. In 95% of the years, participation in this city is between blank and blank inches. Does 95% make you think of anything? Okay, confidence interval? Yes. Or what else? Someone said it. Empirical rule. Where does 95% come up with the empirical rule? So we also call it the 1, 2, or we call it the 68, 95, 99.7. But for what values of the standard deviation? 1, 2, and 3, right? And so 95 corresponds to 2 standard deviations. Now, if you thought about confidence, what's the critical value used with 95% confidence? Which is like 2, right? So either way, you're going to be basically using the same value. You could use 1.96 standard deviations here or 2 standard deviations. Now, 2 is easier to think about. That'd be 6.4 inches, right? So what's 390 minus 6.4? 383.6. And if you add 6.4, it's 396.4. Oh, good. Yeah. Oh, 2 standard deviations, 2 times 3.2. If you use the 1.96, it's going to come out closest to this one. Still, it'll be a little off, but you said number 5? Oh, sure. So are any of these easy or are some of these harder? Because this is important stuff, right? Okay. Yeah, people tend to get cluster and stratified confused, I think, sometimes. Yeah, for sure. Well, which one do you think is cluster and which one do you think is stratified? Well, let's just do them one by one. Won't hurt. City has 5 property classifications: single family homes, apartments, condominiums, temporary housing, blah, blah, blah. Randomly select 10 residents from each category. What kind is that? Okay, let's skip that one because that's a hard one. That's fine. So each property owner has a 5-digit ID number. Use a random number table to choose 40 numbers. What kind is that? Simple random sample. Absolutely. So that's C. At the start of each week, survey every 10th person who arrives at the city park. What kind is that? Systematic. Very good. Yeah. Randomly select 20 city blocks. You know what? I don't think you're going to like that one either. So hang on. We'll come back to that. What about 5, B? Each firefighter surveys 10 of his or her neighbors. That is definitely A, and that is garbage, right? Good. So, okay, good. So you identified what you have more trouble with, and you're like most people, those are the ones that are a little tricky. To me, the difference is kind of structure. I think of a cluster kind of like a handful here, a handful there. Whereas if you think of what the word strata means, it's like different layers of Earth or different layers of the atmosphere, right? There's some kind of structure over just, I'm going to grab a handful over here, a handful over here. And so to me, yeah, well, I like the layered idea. Which one would you say I is? I would say I is stratified. And I would say 4 is cluster. Because a city block here, a city block there, we're not kind of giving any kind of difference between them. We're just saying 20 random city blocks. Whereas we're stratifying in one based on single family homes, apartments, condominiums. There's this division there, right? Yeah. What else we want to take a look at? Sure. Yeah. Oh, yeah. So on this one, all those combinations, does anybody remember the term for that? All the possible outcomes? There's 2 words, both start with S. They end with ample and pace. Sample space. Yeah. All right. Very good. So these are all the possibilities. And it says, what is the probability of getting at least 2 tails? So just count how many have 2 tails. This one. And this one. And this one. Oh, and it says at least 2 tails. So I would also count this one. Did I get them all? I think I did. So how many is that? Out of how many? Out of 8? So sure. Now, if it said exactly 2 tails, then it would have been 3/8. Mhm. Like find the area between 2 points. I could make up one. I don't think I had any on here, but I mean, we use that all the time when we're finding p-values and stuff, right? Yes, sir.
Yeah,
Absolutely, yeah.
and then we've got to zoom.
Okay. Oh gosh, yeah, 18. So if I saw one like this, I would try to check them off individually. January 2005 Gallup Youth Survey telephoned a random sample of 1,028 U.S. teens and asked these teens to name their favorite movie from 2004. Napoleon Dynamite had the highest percentage, with 8% of teens ranking it as their favorite movie, which is true. The population of interest is all U.S. teens. Is that true for that problem? Yeah, right. It's a sample of 1,028 U.S. teens, so we would expect them to find a sample that looks like the population. So yeah, all U.S. teens is probably what the population is. Yes, 8% is a statistic and not the actual percentage of all U.S. teens. Is that 8% a statistic or a parameter? Well, is that 8% talking about the sample, or is it talking about the population? Right. I think you're talking, when you said you're talking about the population, we're going to make an inference, right? Like that's the idea, but you're right. This is about the sample. And so it is a statistic. That's true as well. The sampling design should provide a reasonably accurate estimate of the actual percentage of all U.S. teens who would rank this movie as their favorite. Is that true or false? Yeah, I mean, it's a random sample. The sample is likely to be representative of the population. So that's true. So they're all true. Okay. Yes, what was this one?
Is there a question you could work that would help with the latest significance chapter, chapter 9?
Sure, yeah, I did. Like number,
They didn't have a specific problem.
like number, oh, wait, maybe I didn't. Yeah. Number 2 is a hypothesis test. Chapter 9 is about hypothesis tests. So do they mean 9 or 10?
They said the latest significance chapter.
So, yeah, I think so. We did 2 sample stuff in chapter 10. Is that what you mean, Haley?
I scared her off.
We'll hear in a second, I'm
Okay.
sure.
Yep.
Michaela, did you want me to make up a problem like you were talking about? I have no idea. If you want me to make up one, I will. Sure. So I think looking at previous tests is a great way to study for a final that's comprehensive. Sure. Yeah. So what would happen to the confidence interval if the confidence level were changed to 98%? It started as 99%. And so there's a lot of words in here, but really all it's asking you is if you reduce confidence, what happens to the interval? So if the confidence level goes down, does the margin of error get bigger or smaller? Okay. If we get lower confidence, that is about a smaller margin of error. How do I know that? Well, when I look at the formulas, the confidence level comes into play with the critical value. And when you put smaller levels of confidence, the critical value is smaller, right? And so when you multiply by a smaller number, something smaller comes out. And so I know a smaller margin of error. So this one would say the interval would get narrower. So confidence level and margin of error are directly related. If I did sample size, those are inversely related. Larger sample size, smaller margin. So those are 2 commonly asked type things. What happens when you change the sample size? What happens when you change the confidence level? And if you ever get stuck on something like that, if you had just done one, you could always go back and change it and see, well, what happened? right? If I did it with 95, what happened when I changed it to 99? Did they come back?
Nope.
Haley, if you want to specify, we can talk about whatever. I mean, we probability. Yes, sir. Yeah. Yeah, so this says identify the response variable. And what I think about when I think of response variable is what am I measuring at the end, right? Or when I'm thinking of regression equations, I have explanatory and response. We often look at it in terms of, is this explanatory variable influencing the response variable? So here we have this big experiment involving blood pressure. What does it look like we're going to measure at the end of the experiment? So I think if we look, so they're seeing if this drug makes a difference. So they give these different drugs, and the way they check to see if it makes a difference is they measure change in blood pressure. And so that's going to be the response variable. That's what they're measuring at the end to see if it affects it. And so B. Does that make sense? I think we got about 7 more minutes.
Mhm.
Yeah, what's the definition of a type 1 error? What? Who can tell us the definition of a type 1 error? Well, so they're all okay. Type 1 error, rejecting the null hypothesis when it's actually true. What's a type 2 error? Which is so one happens when you reject the null hypothesis, and one happens when you fail to reject the null hypothesis, right? And so you're right. If you remember one, you remember both. So what would a type 2 be? Perfect. The error of not rejecting the null hypothesis when it's actually false. Honestly, from my perspective, the easiest way to do those is memorize the definition for a type 1 error. And then if you need to, just figure out what type 2 would be because it's the other one. Or if that makes you uncomfortable, memorize them both word for word. I mean, to me, those problems are a little tougher because it's just a terminology thing. And if you don't remember the term, you can't do it. That's the kind of thing that it's harder for me because I have to remember. If we're doing a hypothesis test or a confidence interval, I just look at the formula sheet, right? So I don't have to remember it. But yeah, that's just a word for word I would memorize. Yeah, if we're talking about our regression problems, our explanatory is our independent and our response is our dependent. Very good.
When it says fail to reject the null hypothesis, does that mean it accepts the null hypothesis?
Yeah, so that's a great question. And the terminology is a little weird. It's weaker than that. So we are always either rejecting or failing to reject. We are not accepting. It's very analogous to a criminal trial to where we can either find someone guilty or not guilty. Now, does not guilty mean they're innocent? It doesn't. And for this, it's the same kind of reasoning here. If we fail to reject the null hypothesis, we're not accepting it. We're just failing to reject it. Does that make sense? Yeah. That is a very confusing thing at first. So it's very good you asked that. I say at first. For a long time, it's a confusing thing. Yes, sir. Yeah, absolutely. All right, 13. If I wanted to describe the shape of that distribution, I'd think of it as a dinosaur. And I'd draw a little head on it over here because that's where it seems like it would have a head to me. And so I'd say that's on the left tail. So I'd say that's skewed to the left. And honestly, that really is how I remember it. I think what side looks like it would have a tail, that's the direction of the skew. Mhm. Yeah, so the most common place you're going to be using that is when you are in your formula sheet. When we're doing our p-value for hypothesis test, this is going to come from normal CDF. Uh-oh. It's mad at me.
Uh-oh.
It won't let me write.
Just give it a second. Reset its brain. Now
Oh.
try it.
Oh, neat.
Mm-hmm.
So this has a processor in it?
I don't know. Sometimes it just needs to reconnect.
That's not it. It's charged. Maybe if I switch to a different screen. Oh, you've reached your
Oh.
usage limit.
Oh,
It renews
interesting.
on May 15, 20. Oh, that's soon. Well, I'm going to say it out loud because this won't work now. When we're using normal CDF and TCDF, most of the time at the end here, it's about finding our p-values, right? And so when do we use normal and when do we use T? For means, when we're doing those, it's T, and for proportions, we're using Z. It tells you in the formula sheet, right? When it says you find your test statistic Z equals and you get your p-value from the standard normal table, that's telling you normal. When it says T, that's telling you T. The only time we use the T distribution is for confidence intervals for means and hypothesis tests for means. If we know it's normal, we're going to use normal. And that's for proportions always, and for like a sampling distribution problem of means, or a problem involving means where we know the population standard deviation. I don't know, maybe, let me check and see what it is real quick. So, kind of. I probably don't have time to do this. If you reordered them from smallest to biggest, then we automatically have the minimum and the maximum when we're trying to find our 5-number summary, right? The way we find if there's outliers is we take our IQR, Q3 minus Q1. Do you know how to do that in the calculator? Okay, so it's actually super easy. Do you have a graphing calculator? There's no way you'll be able to use that on your test. Now, do you know there's a lot of places around campus where you can check out a graphing calculator?
Yeah,
Including the math stats.
Okay, good. You just do this. You go to stat. Did you notice when we did it earlier, when we found the standard deviation, the mean of these? If you go to stat and go to one variable statistics, just like we did there, if you look, it gives you the minimum, quartile 1, median, quartile 3, it gives them all to you. But if you're doing it by hand, you put them in order. Min and max are easy. Median is that one right in the middle. So what I do is if there's 10 numbers, I say what's 10 divided by 2? It's 5. And so I'm like, well, there's 5 on this side, 5 on this side. It's what's halfway in between those two middle. And then the Q1 is just the median of the first half of the data, excluding the median. And the Q3 is the median of the second half of the data. Okay. Yeah, I think that's it. Are there a lot more questions? Can we have 5 more minutes?
You can have 5 more minutes.
Okay. They've just got to set up for another review. Oh, yeah. So box plots, each of the vertical lines on a box plot represents one of the 5 numbers in the 5-number summary. So that 310, let's pretend, which one's the actual answer? I don't know. Someone look at the key real quick. It's B? Okay. So if you look at all of those, I can't draw on this anymore. If you look at all of these numbers, the smallest is 310. That's why there's that line right at 310. If you find the quartiles, Q1 is at 510. That middle bar is the median, that's 705. That next vertical bar is 1225, that's my Q3, and the maximum is 3700. Stat, edit, put them in, and then stat, calc, one variable statistics. Yeah. And once you put the numbers in order, it's not really hard to do it by hand either. The first review video I did this week had that in it. I'll send it out tomorrow. Which one? Yeah, so you do Q3 minus Q1, and then multiply that by 1.5. You subtract that number from Q1, and anything smaller than that is an outlier. You add that number to Q3, and anything bigger than that's an outlier. Yeah. So in this one, the interquartile range, I can't remember. I've done it, but I don't remember what it is. Okay, what's 82 minus 65? What's 17 times 1.5? 25.5? All right, tell me what Q1 minus that number is. That's called your lower fence. And anything below that's going to be an outlier. So Q1 minus that number you just told me, the 1.5 times IQR. So anything less than 39.5 is going to be an outlier. And since 35 is in that data set, it's an outlier. If you do that number plus Q3, that gives you an upper bound, an upper fence. Yes, sir. Yeah, probably. Let's see if it's a short or a long one. No, this is quick. So this is a chapter 10 problem where we started comparing two groups. The most important thing you're looking at when you're comparing two groups with a confidence interval is 0. Okay. If 0 is in the interval, so it's like this. What's your name? Xavier. So let's say I'm talking about you and Michaela. My favorite example of this is we seem to have less trouble with money. And so if I ask Michaela how much money she has, and I ask Xavier how much money he has, and I say, I'm not going to tell you how much either one has, but when I subtract, I get 0. What does that tell you about the money you have compared to hers? If I subtract them and get 0. What's the only thing you can subtract and get 0? Well, sometimes. If you have 0, the same number. If you have the exact same amount and subtract, you get 0, right? So if I subtract and get 0, that means you have the same amount. Now let's say let's put Michaela first, alphabetical order. If I say I take the amount Michaela has minus the amount Xavier has, and I have $3. So I took how much Michaela had minus how much Xavier had, and I get $3. I still don't know how much either one of you has, but I now know which one has more. You know which one would have more? Yes, because it's a positive number, right? When you subtract and you get a positive number, the first number is bigger. How much bigger is hers? That's exactly right. And so when you look at that interval, here it says 0.08 to 0.14. Do you notice anything about that interval? That's too ambiguous. Yeah, they're both positive, right? So which one's bigger? P1 or PA or PB? Which one? PA is going to be bigger because they're positive. Remember, if you subtract something that's smaller, you get a positive. So that tells me for sure PB is smaller than PA. By how much? Oh, between 8 and between 0.08 and 0.14. That's how much. Now, if 0 was in there, I'd be like, well, I don't know which one's bigger. It might be this one. It might be this one. If it's all positive, first one's bigger. If it's all negative, second one's bigger. Okay. And so the answer here, since they're all greater than 0, we can conclude that the percentage in favor of legalization in state A was greater than state B. Does that make sense? Ish? I know it's pretty quick. But it really does come down to when we're comparing things, if they're the same, you get 0. If the first one's bigger, you get a positive. If the second one's bigger, you get a negative. That's what it comes down to. I will, and then I think we really do have to call it. Yeah, so 32, I know this is a valid probability distribution if certain qualities are met. What does each probability have to be between what two numbers? No. What? 0 and 1. You cannot have a probability smaller than 0. 0 is okay, but not smaller. You can't have anything bigger than 1, right? Now, all three of those are between 0 and 1. The next one needs to be between 0 and 1. But when we put all of them together, what does that need to be? Yes, their sum has to be equal to 1. Yeah, so individually they have to be between 0 and 1. When you take the sum of all of them, they have to be equal to 1. So how much is left over? 1/10, 1/10, 1/10. How many tenths are left? 7/10. So that's the answer. Mhm. I mean, you could do 1 minus 1/10 minus 1/10 minus 1/10, and it'll tell you 7/10. No, it's both. Kind of like the other tests have been. Structure-wise, it's very similar. Are you going to be able to do your other review with the thing messed up?
Yeah, I've got another iPad.
Oh, awesome. All right.
All right, is that
Very,
it?
very similar structure, just a little longer. It's about 30 questions. Around 5 or 6, I think.